in the beginning, among many things, there was light. And there were many studies done on light. It was in 1638 that Italian physicist Galileo Galilei conducted an experiment to measure the speed of light. But this experiment measured nothing but the reaction time of people. The attempt to measure speed of light came again in 1675 by O. Romer, who based his measurements on the observations of eclipses of Jupiter's moon. Romer calculated the ratio of speed of light to speed with Earth rotates around the sun, which was around 9,300 compared to the modern value of 10,100. But it was in 1809, Jean-Baptiste Joseph de Lambre reported the time for light to travel from the sun to the Earth as 8 minutes and 12 seconds, which yields approximately a little over 300,000 kilometers per second as the speed of light. So what is light? That is exactly the question that Sir Isaac Newton pondered in the 17th century. And he declared that light was a corpuscular, meaning made up of particles. Although there were many questions about this view, it was widely accepted by the scientific community of the time and popularized by his followers. So what happened to light? It was Thomas Young, a young English scientist in 1803 published a paper entitled Experiments and Calculations Relative to Physical Optics, in which he describes the interference properties that light possesses and its similarity to water ripples. And then in 1873, a Scottish theoretical physicist, James Clerk Maxwell, published his brilliant equations proving electricity and magnetism are integrally interrelated phenomena. His 85 pages of derivation, Maxwell was able to find the equation for the electromagnetic wave, whose velocity was approximately the speed of light. And thus was born the classical view of light as an electromagnetic wave, with its electric and magnetic field propagating from one place to another. And light, as an electromagnetic wave, has general properties of a wave, such as wavelength, frequency, velocity, amplitude, and exhibits properties of reflection, refraction, diffraction, and also the Doppler effect. But it was in 1900, the German physicist Max Planck was working on a problem on how radiation an object emits is related to the temperature, and he came up with a formula, which we now call as Planck's law. This formula describes the spectral radiation of an electromagnetic radiation at all wavelengths from a black body at a certain temperature. The only problem was that for this to work, he had to assume that the energy of a vibrating molecule was quantized. The problem was that electrons were being emitted from metal when light was made to shine upon it. And the solution to this problem came in 1905 with Albert Einstein, who explained the photoelectric effect, which was a problem that the wave theory seemed to have. The problem was that the wave theory claimed that the amplitude of a light wave was in proportion to the brightness. So the brighter the light, it should have been easier to create currents inside of a metal, but it didn't. So Einstein postulated that electrons can receive energy from an electromagnetic field in discrete portions. And this was the photoelectric effect, for which Einstein won his Nobel Prize in 1921, which says that electrons are emitted from matter after absorption of electromagnetic radiation. Einstein's theory was later confirmed by Robert Millikan. Thus came the modern view of light as a particle duality nature of light, wave-particle duality nature of light, which says that light has wave-like properties, but modern quantum mechanical description says that it can also be considered to be in particles called photons, which carry energy in packages. Thus, let there be light.